Hey everyone, thanks for hanging with us. Sure. My name is Rakesh Khan. I'm a civil engineer out of North Carolina. A bit on my background, undergrad degree in mechanical engineering, then I spent the first 10 years of my career in geotechnical engineering and construction materials testing. Ran a commercial testing lab for soils, concrete, and aggregate. Did a fair amount of field testing and special inspections that are needed during construction for building code compliance. Then the next 10 years of my career, I spent doing non-destructive testing of aging infrastructure, along with some contract R&D for the federal government, United States federal government. Then about 2.5 years ago, I co-founded Artex with my business partner. And we are focused on field quality control methods for 3D printed concrete, with a focus on field feasible techniques that can eventually start to aid in building code compliance and also in some topology optimization that we're still missing out on because we can't really trust our interlayer bonding all that much. It's a little bit different flavor of presentation from the rest, but for the academics here, I think one of the big takeaways that I'd like you to have is the instruments we're using here are imaging instruments that are probably in your university but not in your building. They have some applicability to hardened and fresh concrete, and we would ask that you consider checking them out. All right, so our presentation here has 4 sections. There's a section on vision, a section on setting, a section on bonding, and then a section on some of our future work. In vision, we're going to just go through a little primer of human and computer vision, how cameras work a little bit. Then we'll talk about recent research. This is where we correlated image data to setting behavior of a commercial 3D printed mortar. Then our ongoing research. This is all funded through NIST. That's the United States National Institute of Standards and Technology. And that picture there is from the NIST lab. And then finally, we'll talk about where we think we can take this kind of technology, ultimately hoping we can come up with a sensor system that can mount to your nozzle and actually give you a printout of the quality of the build that you were able to achieve in the field that day, and also, as these systems become more closed loop, give information back to the printer to start enhancing the quality of the build that is made that day. We think that this also has some pretty exciting applications outside of 3D printed concrete. So again, we're hoping that we can bring awareness to some of these techniques and start to see more research in this field. All right, so let's start with vision. Let's look at these pixels here. So based off of your experience and this pixel data, you know what you're looking at. You know that there are 3 of the same thing. You actually even know what's going on under the surface a little bit because of how your understanding of how this object behaves. Humans are pretty good at this, especially with food. So here's another one. Based off of this surface data alone, we can tell a lot about what's going on in the middle of it. And finally, this one, we can even infer something about how safe it is. Do we want to even eat that? In concrete, it can be a little bit more subtle. This is a picture of the same thin section of concrete right after being placed, as it's approaching initial set, and then when it's pretty much set up. So at first glance, they look a little bit different. We can see some changes in the way that they reflect light. We can see slight changes in color. If we focus down and cheat on this little piece of the concrete that's on the formwork, we can even see that this concrete is definitely set up, and if we needed to do something with it, it's too late. Same kind of goes for looking at concrete in a wall form for a cold joint. So same kind of issue here. We can see some indication that there's moisture loss at the surface. There's changes in the way that it's reflecting light. And ultimately, we can see it turn from wet to what looks to be kind of a skinned over concrete, and finally to a hard concrete that's going to have to come out of that wall form if we never got the next concrete truck there in time. So let's talk real quick about what we're actually seeing here. So the way human vision works, we have some broad spectrum of light. It hits an object. Some wavelengths of that light are absorbed, other ones are reflected to our eyeball. And in our eyeball, the light is focused and goes to our cornea in the back, and there's these three kinds of cells back there. They're different color cones. There's a blue cone, a red cone, and a green cone. So when we look at something, we're actually seeing these slightly different versions of the same image in these different color band passes. If we look at a bead of concrete, we can see that there are some changes in color that we could probably associate with hardness or stiffness. We could see that there's definitely moisture loss in these thin areas on either side of this cut piece of concrete. You can even kind of see these speckles in the top of the surface of the bead that we probably could guess are hard or dry spots in this bead. And that's all from these images that are coming through your eye, these three different images, and your brain is actually putting them all together into a single image. So our eyes are pretty powerful. We use visual inspection to do a lot of kind of pass-fail tests on structural integrity. We've got concrete has a visual assessment guideline. There's one for soil, there's one for lumber, there's even one for welds. But we know that human vision is kind of variable, right? So you guys have probably seen one of these before. This is a picture. I'm told there's a 74 in the middle of that circle. Some of us are colorblind and we can't actually see that. So we have this hardware variability from person to person. We even have this tendency to assign colors based off of assumed context. So this was like a viral picture from years ago where some people thought it was blue and black, other people thought it was white and gold, and it all depends on your assumptions of the context. So how could computers do this better than us? Well, cameras don't really have these problems. And cameras work actually in a lot of the same way that our eyes work. So a broad spectrum light hits an object, the object absorbs some wavelengths, reflects others. Instead of going through an eyeball, they go through a lens. And then instead of having cones, they have these two parts. One is a color filter array, which splits it into blue, green, and red. And the other part is a sensor array, which actually takes the photons that are let through the color filter array, and it changes them into electrons. And the efficiency with which it does that at every wavelength is it's called its quantum efficiency. So for a color camera, this is a typical quantum efficiency with an overlay of the band passes that are involved. For color cameras, the chemical that's used to be the photodiode here to change this from photons to electrons is silicone, but there's plenty of other sensor chemistries out there that react differently in different parts of the spectrum. And there's a lot of spectrum out there. So the spectrum of light that reflects off of objects here on Earth ranges from about 300 nanometers to 3,000 nanometers, and we can really only see a seventh of that, like 400 to 700. A good way to look at that is what is the light that's coming out of the sun? This is a spectral irradiance chart, solar irradiance chart. The yellow curve there is the kind of light that's hitting the top of our atmosphere, and then the orange curve is actually what we would see if we could see everything here, what we would see at sea level. And there's little holes in there because the atmosphere is actually absorbing parts of this light. There's plenty of sensor technologies out there. Like I was saying, silicon is one that works in the visible and the near end of the near infrared range. Another very common one in industrial machine vision is indium gallium arsenide, or InGaAs, and that one works from about 900 to 1700 nanometers, which is completely outside the visible range, but they use it for all kinds of cool stuff, and we'll get into that. So one real quick terminology catch here, near and SWIR stand for near infrared and shortwave infrared. Depending on the camera manufacturer, the industry you're in, the definition of the boundaries of that range will change. So just be careful when you're looking at something that's near SWIR that you actually look at what is the range that they're actually talking about, because it changes. We refer to this range of interest as the SWIR range. So what's out there past the visible range in the near and SWIR? Well, the big one is water. So there are these two bandwidths out in the SWIR range that rather than transmitting water or transmitting photons and looking clear, they actually absorb the photons, so they look like black or dark gray. Those wavelengths are at about 1450 and also 1920. And liquid water absorbs at these wavelengths. At slightly shorter wavelengths, atmospheric water absorbs light, and that's what actually creates a lot of these holes in that graph that I was showing you. Another way to look at this is a reflectance chart. So here the x-axis is wavelength, and the y-axis is how much light got reflected. Depending on how you think about it, it's also how much light has been absorbed. This is actually for geological mineral deposit identification. And you can see that, for instance, calcite has a different signature than kaolinite, which is the deposit that we actually get our calcined clays from. So the way that we generate these kind of images or this kind of data is actually called a hyperspectral approach, when we'll talk about multispectral versus hyperspectral here. So multispectral imaging is where we take an image of an area and we filter it multiple times with different filters and get these discrete kind of chunks of data about what an image would look like in a certain wavelength. Hyperspectral images use like a prism or a slit to spread the spectrum, and they scan one line at a time. So in your 2D array, one dimension represents your horizontal pixels in the line, and the vertical dimension represents all these different spectrum that the line got spread apart after it was pushed through the slit. So if we scan line after line after line, we can actually generate a bunch of pictures at very small bandwidth bins to look at the an image, to look at how it's reacting or reflecting in different band passes. So why do we really care about that? There's already been plenty of study out there on hardened concrete in the SWIR range. This is a great paper, came out of Vienna a few years ago. It's kind of an eye chart, but some notable stuff here. We can see some history in the concrete based off of what it looks like after it's hardened, particularly with water cement ratio and curing conditions, so curing times and even curing temperatures. In early age, we have some pretty good contrast out here in the SWIR range because of its reactivity with water. Things out in the SWIR range, dry versus wet sand, look very different, whereas in the visible range, we know they look different, right? Things that are wet are darker, typically. But out in the SWIR range, there's a big difference between wet and dry and everything in between. With regard to our dry components, cement itself is actually way more reflectant as we get out into this far SWIR range as compared to gravel or limestone sand. So we have some pretty fertile ground here for using machine vision to watch the behavior of concrete. Machine vision and computer vision, again, a terminology catch here I'll just spend 1 minute on. Depending on who you ask, you will get a lot of different definitions of this. If we ask Google, how do these match up in a Venn diagram, you'll see every possible Venn diagram you could think of. And that's because depending on the industry, again, the way they use these terms kind of changes. A good rule of thumb is machine vision is used in industrial settings. It applies an algorithm typically with low latency to control a process or to control quality, like reject defects. Whereas computer vision relies on deeper learning for its algorithms, but that can still be, that description can apply, these two descriptions can apply to the same process. The way we train an algorithm and the way we apply the algorithm can kind of change who thinks what about what to call this. All right, let's jump to settings. So we all know about setting. From the practitioner side, we lean a lot into ACI and ASTMs for collecting data here. So ACI's definition of settings, pretty loosey-goosey, just an empirical value for indicating stiffness as measured by penetration resistance to some method. Two really common methods out there are C403. This is where we use a handheld penetrometer and push these different size plungers into the concrete. And another one is C807. This is one of many VCAT tests where you take a set weight and a set needle and you continuously drop it into your little dish of mortar until it doesn't go all the way down. And you start to get this inference into how stiff it is. The issue with these guys is that they're they don't really work at very early age. They don't really start working until you're a few hours old. A couple other things that we all know about setting. Temperature plays a big part in how fast we are setting. As we move from 50 to 75 degrees Fahrenheit, we get setting behaviors that are twice as fast. And again, if we move from 75 to 100. On the evaporation side, the same kind of issues are present. The hotter it is, the faster we evaporate, and the drier it is in the air, the faster we evaporate. So slight changes can actually really change the evaporation rate, particularly if it's windy. And both of these actually affect the penetration resistance. The evaporation and that interaction with the ambient temperature at the surface of the bead actually causes, in some mixes, the skinning over, where we can see high penetration resistance for a very small amount of distance, and then we fall down into this softer material. And this skinning, we're pretty sure it plays a big part in interlayer bonding. I'll get into what we're doing to look into that. So you'll like this. This is a figure from C403 showing penetration resistance with time. If you notice, it starts at 180 minutes. And from an interlayer time standpoint, this is after we already know that we're going to have to use a bonding agent on layers. But what's happening in these first few minutes, this first hour? And for a scrappy startup that needs to get preliminary data for their proof of concept, we make it happen. So we ended up using washers. We used a select plunger from the C403 kit, left the penetrometer hanging on the wall, and used very small weight increments to track this very early penetration resistance gain. And we could get decent data. The skinning effect in the material that we did a lot of investigation on was pretty prevalent, but we could see this strength gain or resistance gain in the early ages. This first 90 minutes is where we're really trying to focus training any kind of computer vision model on. All right, so we did a few setting experiments as part of a NIST SBIR Phase 1 project. Here on the right, you could see we're collecting some image data in our temperature chamber. The field of view of the camera there is shown there in the top left, top center. And you can see there's this overlay there with these subregions. And what we found is that the behavior of the edges of this bead, where there's more surface area able to evaporate and interact with the ambient temperature, we get slightly different behaviors than the center of the bead, which is a little bit more protected. In this experiment, we took a commercial mortar that you can buy for 3D printed concrete or 3D printed mortar. We manipulated the setting to 3 different rates. Kind of the coldest you would actually pour concrete, something in the middle, and then kind of the hottest you would pour concrete. Extruded a construction scale bead, so that's about 2 inches wide, 50 millimeters wide, and 20 millimeters thick. And then also cast a C403 specimen to do this rudimentary penetration resistance stuff. And we were able to manipulate that setting time pretty successfully. We did it tons of times to get a good idea of how this was really behaving. And we could see that with time, that penetration resistance gain really changes with the temperature. We all kind of know this already. There's a best fit line here that just shows if we try to use time to predict penetration resistance without knowing the temperature, it doesn't work very well. Even in the first 90 minutes, it doesn't work very well. If we look at penetration resistance gain rather than raw penetration resistance, it works a little bit better, but still not very good performance is 71.5% R squared. So this is a real quick statistic that we use as a baseline to say, okay, can we see image parameters that can predict this penetration resistance better than if we just used a stopwatch? So like I was saying, we focus on the center of the bead separately from the edges of the bead, extract parameters using ImageJ. I think I saw somebody else had a screenshot of that. And with some moderate processing, we can come up with some parameters that can predict this penetration resistance gain very closely. So this is predicting that how hard it is to push a needle into this concrete without knowing the time or the temperature history of the mortar. We also wanted to make sure that These things that we're looking at in the sphere don't also occur in the color in the visible spectrum, because if they did, we could use a lot cheaper camera right now. But when we look at these same image parameter extraction and correlation approaches in the visible spectrum, we actually get a little bit worse performance than time. All right, let's move into bonding here. So setting and bonding are related. As that penetration resistance starts to go up, your likelihood of forming a cold joint goes up as well. And a study cited here talking about the actual penetration resistance defines when that cold joint susceptibility occurs. And we know that in hot weather that occurs faster than cold weather. In dry weather that can actually occur faster than humid weather. We're all pretty interested in 3D printed concrete. We know that this interlayer bond is hard to know a lot about from a field practitioner standpoint. This is one of the bigger gaps that we're trying to really solve. In the laboratory, we can control the interlayer time and the temperature pretty well, and we can control what this bond ends up doing. But in the field, we have all these extra factors associated with how it's setting and how it's losing moisture. So we started a new experiment plan with NIST as part of our phase 2 for our innovation research. In this, we are generating these mock prisms that are comparable in size to C348 prisms. So those are the cast flexural strength prisms. They're about 40 by 40 by 160. I haven't seen a lot of presentations on that, but that is what we use as the baseline for the maximum achievable flexural strength. It's basically the ideal flexural strength. It also gives us an idea of what's the variability of even that test, because whatever we predict needs to have its own variability statistics to compare to. In this experiment plan, we're planning to test them in shear and in flexural out of plane on 3 different schemes. So these schemes are focused, one on test method, where we print 9 walls that are all the same with an interlayer gap time that's significantly longer at the mid-height of the wall, so that we're testing just the bond strength at this one place. Scheme 2 is all about the impact of interlayer time when we keep temperature constant. We'll have a little bit of statistics to show on that. And then scheme 3 is actually combining interlayer time and temperature effects at the same time to affect this interlayer bond development, with the idea being that we will image this mid-height wall layer and then try to use that data to predict these bond strengths that we're measuring. And again, this is funded by NIST. So a few pictures from our first regimen. In our first regimen, there are 5 total that we plan to do, where we print these walls and then run through a bunch of tests. In the first one, we did not focus on image data collection. We focused on this print path feasibility and specimen variation to try to nail down exactly how we want to test these. So right now, the prevailing method for testing these is ASTM E518, but there's still a lot of unanswered questions about how to use that for 3D printed concrete with regard to uniformity of bearing conditions, load rate, et cetera, et cetera. So we chopped these up into different widths. We did different kind of profile treatments, capping, trimming, and working with just natural printed profiles. And then we broke these in 4 and 3-point bending. And 2 main takeaways from this work. One is, when we cap these, even if we cap them just a little bit, we significantly change the apparent strength of the specimen. Another big takeaway is, even if you plan it, your specimens, when they're printed in the field, may not actually break where you want them to. So all of these dotted lines here are actually the flexural stress that was experienced in our interlayer of interest when it broke somewhere else. For scheme 2, which is where we varied interlayer time, the x-axis here is the print interval in minutes, and the y-axis is the same flexural strength scale. We tested capped specimens and trimmed specimens. The capped specimens are the blue dots. You can see that they are significantly higher than the trimmed specimens. A couple takeaways here. One is that we do have this loss of strength with time, which we expect. But another takeaway here is that it's not a linear loss of time, and in fact, we believe that this is closer to like a bilinear behavior, where we are transitioning from failure along the interlayer contact to failure through the material from cusp to cusp of that interlayer bead. So those are illustrated here. There's another factor at play there. When we vary the interlayer time, the amount that layer, the bottom layer, compresses will change. So that profile is actually not constant that we draw as the interlayer contact. For our next printing regimen, which we just did 30 days ago, so we got our test strength from these 2 days or last week. We printed through our specimen chambers, which are capable of manipulating the temperature inside the box in between layers. On the left there is just a picture of our specimen chambers laying there on the floor of the NIST Additive Construction Lab. And on the right is a picture of us acquiring image data right there at the mid-height of our test specimen walls. So the idea here is that we will collect image data right after it's been printed, and then we collect image data again right before it gets covered up. And the way that the pixel data there has progressed in that time is really telling us the history of what's happened. So that kind of brings us to future work. There is now a plan to generate about 1,800 training data points that we'll have after we complete these next 3 print cycles. So we have one more with NIST, then we're going to print with a US-based robotic arm commercial printer, and then we're going to print with a gantry commercial printer, along with in one case, their proprietary mix, and in the other case, a commercial off-the-shelf mix that they help develop. We need to move from manual feature extraction into a more machine learning approach, and ultimately into deeper learning approaches as we're able to gather more data. And we really need to move to a sophisticated procedure where we're testing penetration resistance on bead. So we're planning to create basically a robotic arm tooltip that can do these needle penetration tests the way that we think is most appropriate. One of our big concerns with using these conical plungers that are out there is on bead, we can create like a global failure of the bead where the sides push out, and we start to conflate penetration resistance with this overall friction of the bead itself. And then lastly, we need to start to introduce wind in particular. We believe that that's going to create image data that's very interesting because it will no longer be symmetric. We do plan on, like I was saying, mounting this to the nozzle. That's the final version where we can look at what's being printed and what just has been printed and what's about to be printed over. Generating a 360 view of this is at this point like off-the-shelf software. You've probably seen it for multiple cameras that are stitched together for a car. In the case of printing, we would stitch these together, orthorectify them, stitch them, and then segment them based off of what's just been printed and what's about to be printed over. And there are cases where the data that we're collecting outside of those 2 segments could be useful, but as of now, that's kind of out of our scope. And we think that we're on the path here to where if we can get the nozzle-mounted prototypes to predict accurately enough, we can start to generate this documentation about field quality as built. All right, so one of the big question marks right now really is the cost of the components here. So if you are in university and you do go to your photonics lab, or could be in the chemistry department or in a healthcare research setting, you'll find that these cameras are pretty expensive right now. But there is a camera technology that is being developed called colloidal quantum dot, CQD cameras. So these cameras have a lower quantum efficiency than some of these high-grade cameras you'll find in the lab, but they're able to be tuned to bandwidths that you are interested in, and they're expected to become very cheap. They're expected to start showing up in our cell phones. So with the cost horizon of those CQD cameras, we think that a component cost for a system like this could drop below $10,000. If you know what a commercial printer costs, this is just a couple % of a commercial printer. And if you've ever been involved in a job site quality issue that had to be torn out and reconstructed, this costs a lot less than that too. All right, so final takeaways. Cameras can see about 7 times what we can see. Machine vision and computer vision can employ supervised learning models where we can tie physics and we can tie parameters we already know are related to simpler behaviors into that learning. Right now, we're in a development stage for standards in the industry. On the settings side, we know that the methods that are available to us are insufficient, and we need new ones, or we need consensus on how to modify existing ones. Standards for measuring flexural strength, like I was talking about earlier, are also in need of more development and industry consensus on how exactly to do that. We're working with a NIST-led consortium on round-robin testing of these high-volume tests to get statistics on which of these ways of testing is going to give us the most repeatable results. And then our research has shown that we can predict setting progress reasonably well with a commercial mix, and we are currently chasing interlayer bonding, which we know is related to setting, and have pretty high hopes there. So with that, I'd like to thank NIST one last time for their funding here. We also received some funding from the state of North Carolina, also pretty interested in seeing small businesses grow. And I'll open it up to questions.